Good afternoon, everyone.
Afternoon, sir.
I guess up to the previous class, we had talked about the necessity of hydrogeating operation since we were talking like over extensively on the hydro desulfurization part, but as we are regarding your hydrogeating process, so this is not only dealing with your sulfurous compound but also removal of nitrogenous compound like olefin saturation, aromatic saturation, as well as metal removal purpose also hydrogeating can be utilized. So previous day we had talked about some of the basic reactions that is associated with aromatic saturation, olefin saturation, as well as like for denitrification and desulfurization purposes. So, and at the end of the class we had talked about the like what are the catalysts that are currently being used for this hydrogeating purpose, what is the operating temperature and pressures, and based on your feedstock how this pressure may vary from point to point. If you are using naphtha as a feedstock, definitely the pressure requirement will be lower, but as you are going towards like heavier petroleum fraction, that is your residual oil, definitely your pressure requirement is definitely going to vary, as well as because your temperature and pressure will be pretty much dependent on whether you are using a lighter like hydrocarbon for hydrogeating purposes or you are using a heavier hydrocarbon. If you are using heavier hydrocarbon, definitely your temperature and pressure requirement is going to be definitely on the higher side. And we have also told you that what is the purpose of this hydrogeating process. Based on that also you may like choose different types of catalyst. For example, catalyst basically used using like alumina as a carrier, or on the surface of the alumina, which is Al2O3 only, we deposit our catalyst, that is cobalt molybdenum, which is suitable more for your sulfur removal, and for your nickel alumina, which is more suitable for your nitrogen removal as well as for your aromatic saturation purpose. So today we'll be talking a little bit more about the necessity of maintaining like your hydrogen requirement based on the feed that you are dealing with. Similarly, here you can see the desulfurization of straight run naphtha, which is actually coming from your atmospheric distillation unit. For that purpose, your hydrogen requirement for your hydrogeating purposes are definitely on the lower side. So as you can see from this particular chart, as we are going for heavier petroleum fraction, so a straight run naphtha will be the lightest of your all feedstock, so your hydrogen requirement for your hydrotreating purposes also on the lower side. Similarly, as we are going for heavier fractions such as cracked naphtha, then kerosene, diesel, and deep desulfurization will definitely require more like hydrogen compared to your like desulfurization, as well as whenever you are dealing with heavy gas oil. So like your hydrogen requirement will be even more. So the hydrogen requirement ranges between 2 to 10 times the amount of the stoichiometric hydrogen required due to the solubility loss in the oil, leaving the effluent and the saturation of olefins that are produced. So here with this chart we can pretty much understand. So if I ask in the examination, based on the molecular weight of your hydrocarbon feedstock, please give us an idea, provide an idea about the like H2 requirement in your hydrotreating process. So just by looking into this chart and explaining this chart in a proper way, you should be able to answer the question that for heavier feedstock, definitely your hydrogen requirement would be on the higher side. For a lighter feedstock, your hydrogen requirement would be on the lower side. So this is the basic flow diagram of your hydrotreating process, where your your initially your feed is actually hydrogen, which is obviously one of the main reactants for your hydrotreating process, is entering here. So after it is being compressed, so it is passed and mixed with your fresh feed. So your fresh feed is initially entering into your this what should I call it? So your fresh feed and your hydrogen will get heated up, because your hydrotreating reaction is taking place, and obviously the product that is coming out of the reaction definitely would have certain types of temperature, or else the product that is coming out of your hydrotreating reactor will have like significantly higher temperature. So you don't want your temperature or the heat to be lost to the environment. So that is why this heat will be pretty much utilized in order to preheat your fresh feed as well as your compressed hydrogen. So this heat exchanger is placed. So here your fresh feed as well as your uh, this thing, your compressed hydrogen is actually entering, so it is being heated up. So after receiving a little bit of pre heating, so it is entering into the normal heater. So obviously the temperature requirement, you know that the feed is mixed with recycled hydrogen and heated by heat exchanger and by a furnace up to 260 to 427 degree centigrade. So once you have heated this up to that temperature, definitely in presence of catalyst, the hydrotreating process will happen. So the gas liquid mixture enters the top of the fixed bed reactor. So after the heating process is done, your gas liquid mixture is entering to the top of your fixed bed reactor. Gas is pretty much your hydrogen, and the liquid is definitely your feed, because here you are dealing with hydrocarbon feedstock. So that is mostly present in your liquid state only. So your reactant effluent is cooled and separated with gas recycle. So here it is going to be like after heat exchanger, and then after let's say a little bit of wash water will also be used in order to cool it down, and then the separation will take place. So after the separation, at the bottom all the sour water, which the water containing the sulfurous compound will be present. So from the bottom it can be taken out, and the recycled gas or a little bit of hydrogen that might not have reacted properly with your fresh feed, you can actually recycle back to with this hydrogen maker. So part of it can go back to the heater, or a part of it can also, you can directly inject it into the reactor itself to to have a better higher percentage of hydrogen present in the reactor, because you pretty much know that if you are dealing with heavier petroleum feedstock, definitely your hydrogen requirement is going to be on the higher side. So not only you have to mix your hydrogen with the fresh feed, but also you can whatever hydrogen that you have recovered from this separator section, because it is pretty much not sure that whether you would be able to utilize 100% of the hydrogen and would be able to let's say get 100% conversion. So some of the hydrogen definitely would remain as unreacted. So that hydrogen you can directly send to your reactor, or else you can mix it with your fresh feed, and then after a initial heat exchanging operation is done, you can again heat it up, and then you can inject it into your reactor for a second stage of hydrotreating process. So the reactant effluent is cooled and separated by gas recycle. The hydrogen hydrogen recycled to reactor is 60 to 90% hydrogen. It might have this hydrogen recycle. So H2S is removed using amine absorber. So the bottom part of your this separator will go into this stripper column, or which would be definitely separated out. Your this thing will be separated out after the what should I call it, this H2S will be separated out in this amine absorber. So this process reduces sulfur nitrogen to less than zero point 0.5 ppm and metals to non-detectable levels. So not only it is taking care of your hydrogen your sulfur removal, but it is also removing your nitrogen, as well as it is bringing down the let's say your metal percentage present in your desulfurized closure to a almost negligible level, to less than almost negligible ppm level. It will bring it down. So this is all about your entire thing. And the thing is that this stripper section is also there. So stripper actually will help us to because some of the lighter end products might also be present in the from the bottom of your separator section. If those lighter end products might be present, so like whatever that is coming out of from your separator section, so stripper is used in order to remove your lighter end products, so that you can utilize it for other purposes. And from the bottom of this column you will have your desulfurized products. So that is, in the overall, that is your hydrotreating process. So there are several process variables that might influence the hydrotreating operation. So the uh, number one variable, process variable, would be definitely your temperature. So the reactor temperature should be minimized while maintaining the desired product quality. Increasing the reactor temperature will accelerate the rate of coke formation and reduce the length of operating cycle. So can anybody tell me why, if I increase the let's say reactor temperature, why the coke formation will happen? Any random guess? Why, if I increase the reactor temperature, what will happen? Why this coke formation will happen?
Uh, Thermal degradation, I guess.
Thermal degradation, like we are using normal products only, right? But hydrotreating, let's say if I am hydrotreating my naphtha, so under like high temperature, what will happen? Nothing will happen. So it should also be said that your increasing the temperature would be detrimental if you are using heavier petroleum feedstock, such as residual oil or heavy gas oil. So if you are using those type of material, definitely heating to a significantly, keeping the maintaining the reactor temperature to significantly high temperature, let's say beyond 500 degree, may lead to your coke formation. But whenever you are using lighter petroleum fraction, so chances of coke formation would be on the lower side. So it depends on the what type of feed you are dealing with. So required temperature dependent upon the feed rate as well as the quality. So quality, definitely, whether it's a lighter feed or the heavier feed, obviously your required temperature would depend on that. So the rate of increase in reactor temperature is referred to as the deactivation rate. So then comes, after the reaction temperature or the reactor temperature, comes the feed quality and rate. So the amount of catalyst loaded into your uh, reactor based on the quantity and the quality of the feedstock the unit is designed to process. And increase in the change rate will require higher reactor temperature to achieve constant desulfurization or denitrogenation, as well as higher recycle gas rate to maintain the constant ratio of H2 to hydrocarbon. So you can pretty much understand the importance of maintaining your hydrocarbon to your hydrogen ratio. So depending on the product quality, feed quality, it would depend. So reduced feed rate may lead to bad flow distribution through the catalyst, such that the higher temperature will be required in order to obtain good product quality. So reduced feed rate may lead to bad flow distribution through the catalyst, such that higher temperature will be required to obtain your to obtain your good product quality. So you cannot also reduce the feed rate to a significantly lower temperature, or else that might affect the distribution of the catalyst within the reactor itself. So under that circumstances, you may have to operate your reactor at a higher temperature, but higher temperature operation will have its own demerits. So feed rate as well as the feed quality plays a significant role in the performance of your hydrotreating process. Now coming to the, this is the hydrotreating process only continues. So the increase in the end point of the feed will make sulfur and nitrogen removal more difficult, and thus requiring higher temperature, which in turn accelerate the coke formation. So that I have already talked. So the coke deposition also accelerated by the fact that heavier feed contains more precursor that favor coke formation. So I have told you in the first time itself when I was talking about the temperature. So if you are dealing with heavier feed, like heavier petroleum fraction, definitely the chances of coke deposition is going to be more. And whenever you are using this, you might have using a heavier feedstock, and also you have reduced the feed rate. Definitely you might like your desired option is to increase the temperature, and when you increase the temperature, definitely coke deposition will take place. So you have to maintain your feed quality, feed rate, reaction temperature, like reactor temperature, to an optimum level, so that this type of undesired reaction, undesired side reaction does not take place. So reduction in API gravity of the feed for the same boiling range is an indication of higher like higher presence of unsaturated or olefinic product. This type of feed will result in increased hydrogen consumption and higher temperature rise. So you have to understand, this is the one of the very important line that has been written here: a reduction in the API gravity of the feed. So they are saying that if you are not using a, let's say, a significant like moderate level of your API gravity, what does it indicate? So it will indicate that your feed is having higher number of unsaturates. So higher number of unsaturates means higher percentage of olefin presence. So when a olefin is present in your feedstock, so what happens whenever you are adding hydrogen? So the first thing that the olefin is going to do is going to saturate himself, because that has a pretty much higher affinity towards hydrogen. So the hydro treatment process will not take place. Because of this olefin saturation, also there is a chance that temperature within the reactor also may go a significantly higher temperature. So if the temperature goes higher, so the associated like coke deposition problem will also appear. So you see that all of these things are such a way interrelated. If you do not monitor it to the best way possible, so that you see that the quality of your feed plays such a significant role in the hydrogenating process. So if you are having let's say very heavier, like heavier petroleum fraction, means like your API gravity is less than 10, or let's say in the range of like 10 to 20. So obviously that type of feedstock, if you want to process it at higher temperature, coking may take place. If you are reducing the feed rate also, then what happens, the natural tendency is to increase the temperature to make the to do to do this type of this hydrogenating process. So if you increase the temperature, that may also lead to your coke formation. And if your product is having higher percentage of unsaturated like olefins or aromatics products, so under that circumstances also, what you will be needing, you will be needing more and more hydrogen, because hydrogen will first get involved and go for this unsaturated saturation. So olefin will be saturated, aromatics will be saturated, then it will might work out and might work and definitely remove your sulfur or nitrogen. And because of this saturation reaction, also your reactor temperature is going up. So you can pretty much understand the necessity of maintaining the feed quality as well as the feed rate, and the first point that we have talked about, that is the temperature maintenance. So coming to the hydrogen partial pressure, so the hydrogen partial pressure required for operation of a unit is chosen based on the degree of sulfur on nitrogen or aromatic saturation. So here you can see that like what is the hydrogen requirement, so that is going to be dictated by the product quality itself. So what type of product, like whether your product is having like very high percentage of sulfur, whether it is having like higher molecular weight sulfur. So higher molecular weight sulfur, to remove those sulfur, definitely you need like higher percentage of like higher partial pressure of hydrogen. So depending on the product quality or the feed quality, your like sulfur requirement would be varying. So depending on your like degree of sulfur, nitrogen and aromatic saturation, your hydrogen partial pressure like variation will be there. So hydrogen partial pressure is a critical design parameter for achieving desired degree of feed saturation. Increasing the pressure also increases the hydrogen saturation and reduces the coke formation. So they are saying that if you are increasing this hydrogen saturation, so it will actually work out in terms of like in a better way to reduce the chances of your coke formation. So that is one of the advantages of using higher hydrogen partial pressure. So now the third thing is the liquid hourly. Hello.
Sir, how does
Yeah,
it
yeah,
reduces coke formation?
yeah.
Increasing partial pressure, like how does it reduces coke formation?
Because like whenever you are using this let's say hydrogen, so hydrogen will actually not, what will happen, for example, if you are not using hydrogen, so hydrogen what will do, hydrogen is going to saturate the unsaturated product. So if hydrogen is not present, so what will happen, that aromatic, if your aromatic or like olefinic products are present in your feedstock, so if you increase the temperature, there's a first tendency it will directly form the cokes. But if your saturated hydrocarbon like paraffins are present, then increasing the temperature like won't have too much of impact in terms of your coke formation. So because your heavier petroleum fraction has a higher percentage of what should I call it, higher percentage of aromatics or naphthenic products, so that is why it has a higher tendency of forming this thing, what should I call it, this coke formation. Because once you saturate it, it gets converted into paraffinic hydrocarbon, this coke chances of coke formation drastically reduces. You getting my point? If your aromatics and olefins, so this has a tendency to like readily form, this unsaturated hydrocarbons has a like quick tendency to form coke. But if you are dealing with like lighter paraffinic type of petroleum products, even if you increase the temperature, it has a lesser chances of coke formation. You got my point?
Yes, sir. Thank you, sir.
Okay. So now coming to the liquid like space velocity, liquid hourly space velocity is defined as below. So increasing the space velocity reduces conversion, hydrogen consumption and coke formation. So this is like charge rate per volume of catalyst. Okay, so like it would depend on like what is the amount of charging, at what rate you are charging the feed, and with like divide it with respect to the what amount of volume of your catalyst that you are using. So if you are LH like LHSV, which is liquid hourly space velocity, is increased, so that means it is maybe the consumption like conversion may get definitely affected, but the this coke formation will also get reduced, as well as the hydrogen conversion will get reduced because of that. So for average, so the same information I guess I have shared in the first slide itself. So like these are the some of the basic operating condition for your hydrotreating process. Temperature ranges between 270 to 340 degree centigrade, pressure between 690 to 20,000 kilopascal. And so this is the recycle rate consumption of your hydrogen, and this is the space velocity, liquid hourly space velocity would be in this particular range. So at least I guess the basic like process variables and all associated with your hydrotreating process has now been discussed. So I am giving you a clue that might come in your final examination. This process variables, like discussion on this, like how process variables, different process variables influences your hydrotreating process, is like one of the question that has a higher chances of coming in the final FAT examination. So like you have to, like what I have explained, all the stages, how product quality, how rate, how this partial hydrogen partial pressure is actually affecting my like hydrotreating process that I have explained. So like during the examination also, point wise point you have to explain. So don't expect that if you write whatever that is present in your PPT you will get full marks. I am expecting you to explain it also. I have explained the each and every point, what does this mean, what does that mean, so you also have to explain it similar way. So hydrotreating process variables, how like different process variables affects the performance of your hydrotreating process. So if I ask this question, so you have to talk about all of these factors, that is temperature, feed quality, rate, like space velocity and hydrogen partial pressure. So I guess at least with respect to the hydrotreating process we have talked a lot. So this solvent extraction part I will talk a little bit later on. So yeah, solvent extraction and dewaxing, so that is also going to come. So we'll talk about this a little bit later on. Maybe some of the slides we have like jumped over while we are discussing about this hydrotreating process, because up to that Maddox Claus process we are only talking too much about desulfurization process, not talking about our like denitrification, or let's say like nitrogen removal, or aromatic saturation, olefinic saturation. So I thought that maybe talking a little bit about in that respect also will give you some idea why this hydro treatment is pretty much necessary for your petroleum products, not only with respect to your sulfur removal but for other aspects also, that is your metal removal, olefin saturation, aromatic saturation, as well as for your nitrogen removal purpose. So I guess so. This is also talks mostly about your hydro treatment process, but here in this case, the discussion is more inclined towards hydro desulfurization part only. This hydro treating slide. So hydro processing technologies consist of one or like any one of the following. So pre-treatment or hydro treatment of naphtha and gas oil, residue for your catalytic reforming, catalytic cracking, hydrocracking in order to remove impurities like sulfur, nitrogen, and heavy metals. Hydro desulfurization is a hydrogenolysis reaction using ethane thiol, a sulfur compound present in some petroleum refineries. As an example, the hydro desulfurization reaction can be expressed as ethane thiol reacting with your hydrogen, producing ethane and hydrogen sulfides, and then you have to further purify your hydrogen sulfide. So the catalyst used for this type of hydro treatment process is many metal catalysts catalyzes this HDS or hydro desulfurization reaction, but it is those in the middle in the transition metal series that are going to be more active with respect to this hydro desulfurization. So like ruthenium disulfide appears to be the single most active catalyst, but binary combination of cobalt molybdenum are also highly effective. So here I have also, whenever I was talking about the this hydrotreating process, we have talked about this cobalt molybdenum combination also. In practice, most units in most HDS unit in petroleum refineries use catalyst that is based on cobalt modified molybdenum disulfide together with a smaller amount of other metals. Aside from this, MOS2 catalyst, nickel and tungsten are also used depending on the nature of the feed. For example, nickel wolfram catalysts are more effective for hydro denitrification, which is also desired in many hydro desulfurization units. So like other than your nickel molybdenum catalyst, nickel wolfram catalyst, you can also utilize for hydro denitrification purposes. Yeah, so in an industrial desulfurization process, the hydro desulfurization reaction takes place in a fixed bed reactor at an elevated temperature ranging between 300 to 400 degrees centigrade. The elevated pressure ranging from 30 to 130 atmosphere, typically in the presence of catalyst consisting of a base impregnated of cobalt and molybdenum. So that base is what we use, that is why you use alumina as a base. On that alumina we impregnate this cobalt and molybdenum, or for your denitrification purpose also nickel wolfram or nickel molybdenum also you can impregnate. So the liquid feed is pumped up to a required elevated temperature and is joined by a stream that is rich in hydrogen. So that we have talked about when I was talking about this hydrotreating process. So the liquid feed is going to be mixed with this elevated pressure, this hydrogen rich recycled gas. The resulting liquid gas mixture is preheated through a heat exchanger. So this process only I'm going to talk about here. So just a minute, wait for a moment. uh, just a minute. Yeah, so the resulting mixture is preheated by flowing it through a heat exchanger before the it enters into the heater section. So the preheated feed then follows into the fuel fired heater, where the feed is totally vaporized and heated to required elevated temperature before entering the reactor. Reactor means the fixed bed catalytic reactor only, flowing to a fixed bed of catalyst where the hydrodesulfurization process takes place. The hot reaction products are partially cooled by flowing it through heat exchanger, definitely, because product will have a significant amount of heat that is present in it. So that is why your fresh feed plus your compressed recycle H2 gas is going to be preheated using the heat of your product. So the hot reaction products are partially cooled by flowing through a heat exchanger where the reactor feed is preheated, then it flows to a water cooled heat exchanger before it flows to a pressure controller and undergoes pressure reduction down to about 3 to 5 atmosphere, because your reaction is taking place between 300 to 400 degrees centigrade, and the pressure is also between 30 to 130 atm. So like after this process is done, so after it passes through your pressure controller, so the pressure comes down to 3 to 5 atmosphere only. So the resulting liquid gas mixture enters the gas separator at about 35 degrees centigrade and 3 to 5 atmosphere of absolute pressure. Now the most of the hydrogen rich gas from this gas separator vessel is recycled gas, which is routed back to a amine contractor for removal of let's say, because your hydrogen may contain a little bit of like hydrogen sulfide, so it has to be properly treated in this amine contractor. So the routed through an amine contractor for removal of reaction product, your hydrogen sulfide that it contains, your hydrogen sulfide free like your hydrogen gas is going to be recycled back for reuse in the reactor, or a part of it you can also mix it with your fresh feed and pass it through the heat exchanger, and then again you heat it, then you pass it through the your what should I call it, your reactors, your heater section, and then you enter it into your like fixed bed reactor. So both option is available. So hydrogen free H2S free hydrogen rich gas is then recycled back for reuse in the reactor section. Any excess from the gas separator vessel joins the sour gas. Sour gas is obviously going to contain your H2S from the stripping section of the like stripping section of the reactant product liquid. The liquid from the gas vessel is routed through a reboiled stripper like distillation tower. The bottom product from the stripper is the final desulfurized product from the hydrodesulfurization unit. The overhead sour gas from the stripper contains hydrogen, methane, ethane, and this hydrogen sulfide plus propane, or a little bit of butane it may also contain. So I'll just show you the figures. So they are talking about the light end product that is coming out of this unit, this stripper unit, because here you are using steam as a heating medium, and definitely this is none other than your distillation process only. And this gas not only contain your hydrogen and a little bit of like hydrogen sulfide, but also may contain this other types of your hydrocarbon products like propane, butane, methane, or ethane. So like the sour gas is sent to refinery central processing plant for the removal of hydrogen sulfide in refinery's main amine gas. So like through this amine treatment, your this sulfur dye is like H2S is going to be removed. So like main amine treating plant, through a series of distillation towers for recovery of propane, butane, and pentane, or heavier components, the residual gas H2, methane, and ethane, or some propane, you can utilize it as a fuel gas. The hydrogen sulfide removed and recovered by the gas treating plant is subsequently converted to your elemental sulfur through the Claus process. So rather than your oxidation is taking place, so like your H2S is finally getting converted into Claus process. The sulfurous compound from your HDS feedstock, this refinery HDS feedstock, that is naphtha, kerosene, diesel, and heavier oil, contain wide range of sulfur compounds, that is thiol, thiophenes, organic sulfide, disulfide, and many others. So these are the some of the products that are going to be processed in this hydro treatment process. So this flow diagram and the flow diagram I have discussed here, I guess at the end of your at the beginning of our class, is almost the same. Only that flow diagram is a little bit of detailed. It has been explained, and the light end separation is not mentioned here. But in that this particular flow diagram, the light end separation is also mentioned. So the remaining part is almost the same only. So the same process, like the same hydrotreating that we have discussed there, the same thing is happening here also. So like not much difference is there. So you can see here your feed is entering, and through this channel your your recycled hydrogen gas is entering. So like either you can compress your fresh hydrogen, you can get it from other resources, or whatever hydrogen that you get from your gas separator, because gas separator, it is not in 100% sure that you are being able to utilize all the hydrogen in order to remove the sulfur. So some of the hydrogen gases definitely would remain unreacted, and this gas may also contain a little bit of H2S present in it. So that is why this amine treatment has to be done in order to remove any sulfur from your hydrogen product. So you see that your feed is entering here. After you have compressed your hydrogen gas, it is entering into your heat exchanger. Heat exchanger is doing what? It is doing nothing. It is actually utilizing the product that is coming out of my fixed bed catalytic reactor, where our hydro treatment process is actually taking place. So here the heat exchanger is heat transfer is taking place, where your feed and your recycled hydrogen rich gas is getting heated up. Then it is entering my fired heater, where it would be it is going to raise the temperature up to 300 to 400 degree centigrade. And we have already added compressor. So your pressure is already high in this case, so your pressure may vary between 30 to 130 atmosphere. And then once it enters into your fixed bed catalytic reactor, so that is where your catalysts are going to be stored. So from the bottom of this your fixed bed catalytic reactor, your product stream is going to come out, which is obviously other components will also be present, but obviously desulfurized products will also remain in this stream. So it is passing through your heat exchanger, where your feed plus your hydrogen is being heated, and then it is passing through this pressure controller, where from 30 to 130 atmospheric pressure, your pressure is being reduced to your 3 to 5 atmosphere. And we are using a water cooler, because my because my reactor product temperature is in the range of 400 degrees centigrade. Definitely we cannot allow that temperature to leave the system. It has to be cooled down. So that is why after cooling and after reducing the pressure, it is entering into my gas separator. And because only when your system is at a lower pressure, then only you will have a effective gas separation. That is why this pressure is mandatorily reduced. Hello, who is this?
Hmm. అది బయట పెట్టుకోవచ్చు.
Just a minute. I don't know who is this guy. Is anybody? I don't know, because within the, please can you hear me? So please mute your microphones. So now you see, because for your gas separator to operate, you need to reduce the pressure to a significant level, or else, because in your, if you are increasing the pressure and you are having a liquid, obviously the gas is going to be dissolved in that liquid. so you do not want the gas to be dissolved, and because that gas may also contain significant amount of H2S, so that gas like H2S gas, you cannot pass it through this gas separator. So by reducing the pressure and the temperature, we are making sure that the lighter gases like hydrogen or H2S gases are partly separated from here. So gas separation will take care of the gas. This gas will pass through this amine contractor, where lean amine is going to be implemented in order to take care of my H2S. So my the top product, the top gases is that is going to come out from this amine contractor is definitely going to be a sulfur free gas. So once this sulfur free gas is, then again it has to be passed through a compressor, because our pressure requirement in the fixed bed reactor is 30 to 1 atmospheric pressure, like 130 atmospheric pressure, and the bottom part of this liquid stream is going to come to this stripper, where heat steam is going to be utilized, and definitely using that steam. So this is none other than a distillation column only. So from the top your gases is going to come out. So this gas may definitely contain different types of hydrocarbons, starting with methane, ethane, propane, butane, and definitely a little bit of H2S product might also be present. So all of this gas will be combined together, the gas that is coming from your gas separator and the gas that is coming as the top product of this stripper section will be combined together. You can directly send to your different stages of distillation, where you can separate out your what should I call it, separate out your sulfurous compound from your your hydrocarbon like propane, ethane, butane, or heavier hydrocarbons, and the H2S product that, or the sulfurous product that you will have, definitely you have to pass it through Claus process in order to convert it into a elemental sulfur. And the bottom part of this condenser section will have this reflux drum, and definitely a little bit of water production will also take place, but this water will also contain a significant amount of sulfurous components. So that is why it is called as the sour water, and the bottom of this stripper section is going to give you this desulfurized product. So that is all the the entire flow diagram of your hydro treatment or hydro treating process, so whatever you wanna call it. So so whatever I have discussed in this, through this particular small diagram, so the diagram is only has been extended or more elaborately explained here. So the same, this diagram and the diagram just now I have discussed today now, so these two diagram are the same only, but whenever you are talking about the process flow sheet of this hydro treatment process, definitely you should talk about this diagram. So that diagram is explaining the process in a very very easier manner, but if you want to understand the process, what are the components that is present there, definitely this diagram is more appropriate. So I guess what are the utility of all of these components I have properly explained now. So similarly, hydro treatment process flow diagram, if I ask in the exam, you have to draw this diagram and explain the process, individual steps, why how this heat, what is the purpose of this heat exchanger, purpose of this fire heater, why we are using gas separator, what is the utility of your pressure controller, as well as this water cooler. So all of this thing you have to properly explain, as well as you have to give the this particular flow sheet that is associated with your hydro treatment process. So with this, I guess our hydro treatment, hydro denitrification, aromatic saturation, olefinic saturation, all of this part is done and dusted. Now only that part is remaining in this particular module is the discussion about your solvent extraction and dewaxing, which we are going to talk about in the next class. And I am thinking about asking in the for your this examination, for your quiz, I'm going to ask all the question from your module number 5, not from the module number 4. So I'll just post this PPT today itself in the Microsoft Teams file section, as well as in the course page. So just you can have a look through it, because or else what will happen, our cat 2 is also we are going to only talk about this module 3 and module 4. So it would be better if we can cover up this module file through our quiz too. So our quiz will be happening on next week by Thursday's class. No, not by Thursday. I'll take it on Wednesday itself. Should I take it on Thursday or Wednesday? So this option I am giving you.
So
So
you
because
said 12th,
yeah,
I think.
no, 12th I'll not take it. I'll
Okay.
because this thing I'll only going to finish by maybe next class or by Monday itself. So like I'll give you 1 or 2 days to prepare for it. So once it is prepared, then I'll take this test. So I'll take
So
it
we have a
on
class tomorrow though.
Wednesday. Wednesday.
Yes, sir. Okay, fine.
Wednesday I will take it. Okay. So maybe some topics might get left out in the next class, so that I have to finish it off by Monday's class, and Wednesday we'll have this. So the
We have a
syllabus
class
for your
tomorrow
quiz
as well,
too.
sir.
So tomorrow we have a class. So
Yes, sir.
tomorrow I guess I don't know whether I'll be able to entirely finish it off, because you see that talking about the hydroheating, it almost took the entire class. So here I have to talk about solvent dewaxing, and also this part might take a little bit more time. So like for our safety purpose, I'm keeping 2 classes to complete this module, and on Wednesday we will take this module 5 for our this quiz too, and so by next 15 days your entire syllabus will be completed. So my target is finish the syllabus as soon as possible. Okay. So I guess whatever I have talked about, I guess is pretty much loud and clear. So if you don't understand it after the this cat examination, I may also take 1 or 2 classes to give you a recap on this module 5 if you want. So like whatever till what I have talked about up to today's class, so this purification of petroleum products, because this is one of the most important modules of your entire petroleum refinery. So like did you understand what I'm talking about, step by step, like flow diagram that I talked about today? Did you understand it? Hello.
Yeah.
Yes, sir.
Yes, sir.
Yeah, if
Yes, sir.
like if one more classes is required, please let me know, because I'm not in hurry, because we are already done with 5 modules, so the remaining module may take only 2 weeks time to complete. So not a like we don't have too many things to cover. So like if you want a class on this, a repeat class on this, I can also do that, but I don't think it would be required. Okay, so in the next class, our target would be to finish off this solvent extraction part and conclude this module, and maybe one recap class I'll take on Monday to finish it off, and then we'll have our class test on Wednesday. Thank
Yes,
you
sir.
all for attending today's class. Just go
Excuse
and
me,
answer the poll question. Yeah,
sir.
Sikha?
The flow sheet we have discussed today, like
Yeah.
we can see the other processes, denitrification and other metal extraction and
Yeah,
all.
yeah.
So, like, are they included in hydroheating,
Yeah.
or like
They are
we
pretty much
use
included,
other
because they are using only one catalyst to treat all the this thing. Because
but
for like I have told you na, that the most preferred, for example, if I want to take out your sulfur, the most preferred option is to use your cobalt molybdenum catalyst on alumina. But since if your target, for example, it will depend upon what type of product you are using. If your product is having higher nitrogenous compound more than your sulfurous compound, definitely you have to go for nickel wolfram or nickel molybdenum on alumina, alumina, take alumina as the base. So like you have to choose your catalyst based on the composition of the feed or the quality of the feed. So like only one process is more than sufficient to take care of all of these things.
so
Okay.
like the process flow sheet remains same, but we
Yeah,
just change the
process.
catalyst.
Yeah, only the catalyst will change.
Okay. And sir,
Only the catalyst.
the other sulfuric compounds like mercaptans and
Yeah.
these,
So
like,
mercaptans I will use Medox process. Done and dusted.
so
That
like
we have already talked.
that is we do have another units, like separate units for
Yeah, yeah,
doctors.
yeah, 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 yeah.
It is not included
Merox
here.
process, no, Merox process will definitely we have to go for when we are dealing with this kerosene products. So you kerosene, you see, okay, let me just go back to this thing. So can you see the flow sheet? Flow sheet, so page number
No,
6. Page number 6.
no, sir. Like I can see page number 40.
Right? You can see na page number 6.
I don't
Yes,
know,
sir.
sir. Maybe the internet is like.
What? Other people can see it.
Yes, sir.
Yes.
Page number 6.
No, sir.
Yes, sir. Yes, sir. It's visible. Page number 6 is there.
Yes, sir.
Is it visible na? So you see, if I check this particular unit, this because we started with this flow diagram only because I was saying that whatever product that is coming out of my refinery either has to go through amine treatment, Merox treatment, Klaus treatment, or whatever desulfurization that we are, or hydro treatment that we are talking about. So you see, corresponding to my jet fuel and kerosene, Merox treatment will have to, like, we have to go through the Merox treatment. So because your jet fuel and kerosene has a higher chance of containing your this mercaptan type of sulfurous compound, so that is why Merox treatment is mandatory for those cases. So you see that the gas that is coming from out of your atmospheric distillation unit, this gas, so this gas may also contain like your mercaptan type of component. So for that purposes, Merox treatment is definitely desired. So like depending on what type of feedstock that you are handling and what type of like sulfurous compound might be present in that particular petroleum fraction or gaseous product, so depending on that you have to use different types of treatment. So Merox treatment would be mostly preferred for your jet fuel and kerosene treatment, and hydro treatment would be preferred for your naphtha treatment, for your diesel oil treatment, as well as for your light naphtha treatment. So you get my point, right? Depending on what feed, like what type of petroleum product that you are dealing with, your treatment process will vary. Hello.
Yes, sir. Got it, sir.
Can you see the slide page number
Yes, sir.
6,
Now
right?
I can see. Yeah.
So that is what I am talking about.
Yes, sir. Got it.
Okay.
Thank you, sir.
Okay.
Thank you, sir.
Okay. So like this theory subject is boring only na. So how I am teaching, you people are not understanding, only just shaking your head, or like you people have understood what I am saying, what I want to say or discuss. Well, just a general feedback, because like theoretical subject, if you don't understand it, it becomes a very repetitive and very boring. So like so far you people have understood, because it's a theoretical subject, that's why I pretty much need your feedback, because I also need to like maybe change the way I am teaching a little bit to make it more interesting. So like so far you people have understood what I have, like whatever flow sheet, flow diagram, why each of these units are utilized. So have you understood it, right?
Yes, sir. Yes, sir. We understand.
Okay. Feedback, student feedback is pretty much needed. Okay, chalo, bye. Okay, see you all on tomorrow's class.
Bye, sir.
Thank you, sir.
Thank you, sir.
Sir, I have a doubt, sir.